Okay, in this video I'm going to review what goes on at a chemical synapse. I put a couple videos from YouTube on the Blackboard site, and also you can go back and review the motor neuron stimulating a muscle. That also reviews a chemical synapse. So just to go through it, overall, what's going to happen is depolarization from an action potential is going to come down the axon and lead into the axon terminal. What's then going to happen is, when that action potential gets down to the axon terminal, calcium from outside is going to rush inside the axon terminal. And what it's going to do, it's going to cause the binding of these synaptic vesicles to the cell membrane. Now remember, these synaptic vesicles are filled with neurotransmitters, which when bound here, the neurotransmitters are going to be released, and they're going to bind to receptors on the next neuron. This could also be a skeletal muscle cell, cardiac muscle cell, other organs. And then when that neurotransmitter binds, it's going to cause a change. It's going to cause a change in this cell. Now the other thing that has to happen, remember, and we talked about this with muscles, is when that neurotransmitter binds, it can't just stay there. It can't just stay there. So what's going to happen is it's going to be broken down, most likely by an enzyme. So that neurotransmitter will bind, cause a change, and then be broken down. What will happen in many cases, in order to recycle these neurotransmitters, remember, these neurotransmitters can be reuptaken back into the previous neuron, the presynaptic neuron. So in the case of acetylcholine, if you remember, there's an enzyme, acetylcholine esterase. Remember, ASE means it's an enzyme. Breaks it down, and it's either broken down or it's reuptaken. The reason this is important to understand is that many medications will actually affect how well drugs are reuptaken back into the presynaptic neuron. So, action potential comes down, calcium comes in, binds or causes a change in synaptic vesicles that binds it to the cell membrane. You get the release of the neurotransmitter, and it binds to a receptor. Now, one thing I want to emphasize, which I haven't talked about much, is some of these neurotransmitters are going to be excitatory, which means when those neurotransmitters are released and bind, it will cause an action potential to be generated in this next neuron, or in a muscle cell, cardiac muscle cell, skeletal muscle cell, or an organ cell. But there are also neurotransmitters that are inhibitory, and these are just as important. What happens with them is they bind here, and what happens is it stops an action potential from being generated, or it decreases the chances of a neurotransmitter, of an action potential being generated. So inhibitory neurotransmitters, they will decrease the chance of getting an action potential in this next neuron. Now don't think inhibitory neurotransmitters are bad. They're good. We need to control things. We need to be able to stop things from firing. Sometimes we need to excite them, but sometimes we need to inhibit them. So it just depends on the situation. So inhibitory neurotransmitters aren't bad. They're actually doing their job. Here's a review of what I just went over. So you can read that on your own. Okay. I want to talk about something called synaptic potentiation. And what this is, it's when the synapses between neurons are more likely to fire. Let me give you an example. Most people think the brain is pretty inflexible, that you have these synapses and those are the synapses you have and things don't change. And in reality, that's not true. Synapses can become stronger. So if this is a neuron, this is the next neuron, and so on, and you have these synapses. Okay? If I asked you guys, can you give me your phone number? You guys could just give me your phone number very, very quickly. Why is that? Well, memory is based on synapses. So when you remember something, you're forming synapses in your brain. Well, if it's something that you've done over and over and over again, that pathway, that memory pathway is very strong, And that's because of synaptic potentiation. Now what happens, let me show you here, if you use a synapse over and over and over again, they have found that it will actually increase how strong the synapse is, which means it's less likely to go away. Now, why would a synapse go away? Well, let's say I gave you my phone number, and you couldn't write it down. I just told you you had to memorize it, and you were going to call me tonight. So I give you my phone number. You go over it in your head over and over again. You're forming synapses to form that memory. So you call me that night, we talk about whatever, and then I ask you 2 weeks later, what's my phone number? You probably won't know it, and the reason is because while you form those synapses initially, if you don't use them, then they're going to break down. Your brain's going to use its energy in a different way. But if it's something like your own phone number that you've done over and over and over again, then that synapse becomes much stronger. And the reason they think that is because the calcium levels increase when you use a synapse over and over again. So you get more neurotransmitter, that synapse becomes stronger. A good example is someone with Alzheimer's, early stage Alzheimer's. If you ask them, if you introduce yourself to them and you give them your name, 10 minutes later they might not be able to remember it because they weren't able to form new synapses. But if you ask them something that happened 20, 25 years ago, in early onset, or not early onset, but in early stages of Alzheimer's, they still remember it. They still retain their long-term memory, and that's because of synaptic potentiation. The other place you see this is in the issue of chronic pain. Now, this isn't as positive as with memory, but if someone has a pain pathway, if they've had pain for a long period of time, or if the pain was really, really severe, then what will happen is that pain pathway to the brain will stay there. And once that pain pathway is there, it's very hard to get rid of. It's hard to medicate, and that's what we call chronic pain. So those of you going into health fields where you'll be dealing with people that are in pain a lot, you need to make sure that you control that pain so they don't get this pain pathway that becomes difficult to stop. And again, we'll talk about this later, but you don't feel pain till it gets to your brain. So there's a pathway with synapses there that sends the signal to the brain. All right, so synapses are always changing. So what I mean by that is you may see changes in the amount of neurotransmitter that's released. You may see differences in the number of receptors. Those can constantly change. You can also be born with a different amount of neurotransmitter or a different number of receptors. So we're going to talk about the effect that drugs have on synapses. We'll do that in class. All right, I'm going to go through basic examples of different neurotransmitters. Understand that what I'm telling you is very simplified. Neurotransmitters can do different things in different parts of the brain. They're constantly modified, and neuroscientists are constantly finding new things that neurotransmitters do. The first one's acetylcholine. Now remember, they can be excitatory or inhibitory. We already talked about this when we talked about muscles. Acetylcholine is excitatory to muscles. So when acetylcholine binds to a muscle cell, a skeletal muscle cell, it's going to induce or increase the chances of muscle contraction. But it's also found in the central nervous system, and it's involved with memory formation. The hippocampus, which we'll talk about or you'll review when we go through brain parts. So what happens in people with Alzheimer's, the amount of acetylcholine found in the hippocampus goes down. So they're not able to form short-term memories. Okay, they're not able to form short-term memories. Serotonin is inhibitory. Now again, this is not a bad thing. Serotonin is involved with mood regulation, sleep levels, appetite, migraine headaches. When someone takes ecstasy, what it does, it's enhanced by ecstasy, so you get more serotonin. You get more serotonin. In someone who's chemically depressed, here's a neuron there, and there is the next one. In someone who's chemically depressed, what happens is the amount of serotonin they have going through this synapse goes down. So what Prozac and Zoloft do is when serotonin's in the synapse, what they do, remember it's going to be reuptaken, is Prozac and Zoloft inhibit the reuptake. They inhibit the reuptake of serotonin, which increases the amount of serotonin in the synapse and decreases that chemical depression. Ambien also influences serotonin, and one thing that they found, and one of the other reasons, another reason chronic pain needs to be controlled, is that in people that are in that constant pain, which is over 3 months or over 6 months consistently, what happens is their serotonin levels actually decrease in their brain, which can lead to depression in people with chronic pain. Dopamine is one you're going to hear a lot about. It can be excitatory or inhibitory. It depends on where you're talking about dopamine, depending on what it does. It's involved with the pleasure pathway. The pleasure pathway is a pathway within your brain of neurons that make you feel good. It could be something doing something you enjoy, eating something you enjoy. It can also be involved with drugs, illegal and legal. Sex can increase dopamine, eating can increase dopamine and stimulate this pleasure pathway. So when people become addicted to drugs, what happens is this pleasure pathway is being stimulated by those drugs. And when they try to come off the drug, that ability to feel good is negated. Now, in Parkinson's disease, we talked about over here how acetylcholine stimulates muscle fibers to contract. Dopamine, when it's secreted from a certain part of the brain, inhibits muscle contraction. So I want you to think about what happens with someone with Parkinson's disease. What is the symptoms? One of the symptoms is a constant shaking. And why that happens is because they're not secreting dopamine, and so those muscles are not being inhibited the way they should be. So again, in this case, the inhibitory part of dopamine is also important. Now, the reuptake of cocaine is inhibited, or the reuptake of dopamine is inhibited by cocaine. So what happens when someone takes cocaine, the dopamine stays in the neurotransmitter or stays in the synapse longer. It stays in the synapse longer and gives that person that high. They've also found in people with schizophrenia, they have increased dopamine levels. So if you think about symptoms of schizophrenia, hearing voices, seeing things, that's caused because of this increase in dopamine in certain regions of the brain. Norepinephrine is another neurotransmitter that makes us feel good. When you take amphetamines, it increases the effect of norepinephrine. Here's the pleasure pathway I talked about. So when someone does something that makes them feel good, and it doesn't have to be illegal drugs, it can be just something that makes you feel good. This pathway, again, you have synapses through neurons through this pathway that make you feel good. A couple more examples. Gaba, which is actually an abbreviation for a long neurotransmitter. I'm not concerned that you know the big name. It's inhibitory in this central nervous system. When someone takes or drinks alcohol, what happens is this neurotransmitter becomes more prevalent. So what happens is things slow down. People don't think as well. They don't have as good a reflexes, so their driving is going to be affected. So alcohol affects the amount of GABA in the brain. Glutamate is really important for learning and memory. I'll show you later how it can cause difficulties, though, in the case of someone having a stroke. I'll go through that with a visual aid in the next couple slides. Endorphins. Endorphins are your natural feel-good hormones, or neurotransmitters. We talked about dopamine makes you feel good. Endorphins make you feel good. They're your natural opiates. You usually hear about people that exercise a lot. It almost becomes an addiction. What happens when people exercise for an extended period of time? They produce more of these endorphins, which makes them feel good. So if they have to stop exercising, or they do stop, they can sometimes feel slightly depressed or just not as good. Another thing endorphins do is they can inhibit pain. So when endorphin levels go up, pain sensation tends to go down. Some people with chronic pain use what's called a TENS unit. This can be put usually you see it in the lower back. What it does is it stimulates, you feel a vibration, a little electricity is being conducted in that TENS unit, and they've shown in people and in studies that this decreases the pain sensation. They don't know exactly why it works. It could be because it's stimulating endorphins, which makes the pain level go down. It could also be that it's blocking the sensation from getting to the brain, the sensation of pain from getting to the brain. Now, endorphins are mimicked by drugs like morphine, heroin, and methadone. If you look at these drugs, these are some of the most addictive drugs that exist. So if you take these drugs and your endorphin levels go up significantly, obviously it's going to make you feel good. But I will also tell you that heroin, especially heroin and morphine, are two of the hardest drugs to come down from or to stop taking because they affect your brain in such a strong way. This is what I was talking about with glutamate. What they found is when someone has a stroke, which is going to start to interfere with neurons functioning or killing neurons, what they have found is, let's say this neuron has been really affected by the stroke and is going to start to die. As it starts to die, what it has a tendency to do is to release large amounts of glutamate into its synapses. And when it does that, it then has an effect on the next neuron. And glutamate at really high levels will actually then start to cause this neuron to start to die. And then when it starts to die, it will do the same thing. It will go down to the synapses and release large amounts of glutamate. So what this causes, they think, is that when someone has a stroke, the day of the stroke, you might not see a lot of negative effects from the stroke. But as it goes on, after the stroke, 24 or 48 hours after the stroke, then you start to see increased problems due to the stroke. And they think it's because of this glutamate cascade, that one neuron sending another signal to another neuron when it starts to die. When it starts to die, then causes the next neuron to die, and it can spread from the initial part of the brain that's been injured. So one of the things scientists are trying to do is trying to find a way to decrease this glutamate cascade that occurs with a stroke. The problem is, if you go back to what we talked about, glutamate's involved with learning and memory. So if you just cut off all the glutamate, obviously that's going to have negative side effects on the brain. I will leave you with this picture. We'll talk about drugs and what they do to the brain, but here's a little kitty cat having a cat overdose. It's a kitten, so he probably just got tired and went to sleep. So that's the end of this video. So again, go back and make sure you can do match the neurotransmitters with their functions.